Welcome to my presentation, and I first of all want to welcome my dear colleague Big Nok Wu for
Hello.
being a podcast partner in this presentation.
Hi everyone, I would like to introduce my colleague Fabian Wein, who has recently published a review article with two other colleagues about feature mapping, and today he is here to provide some insights to us into numerical integration within the framework of feature mapping. Welcome, Fabian. Please go ahead.
Thank you very much. Feature mapping are these kinds of methods where we have a higher geometric object, which is parameterized, and we map it to a fixed grid in the previous form. There are meanwhile a wide range of methods available of different kind with a lot of common features. And together with Peter Dunning and Julian Norato, we wrote this review paper. And in this review paper, we also propose a common name for this class of structural optimization. And the name we propose is feature mapping.
Fabian, could you shortly describe or give an example how you would parameterize such a feature?
This feature here is parameterized by the endpoints. So we have the 4 coordinates. One could have also the width of the feature, but here it's only the endpoints.
Okay.
This is a benchmark example I use for the most part of this presentation. So it's an elastic problem. We have a single vertical bar, which is parameterized by the variable s. When s is small, we have a very good compliance. When s is large, we have a stupid design with a very poor compliance. And now we want to model this by feature mapping. So that means we do not have the idealized analytical position of the bar, but we need to map it to a fixed grid. And this mapping we do first with a naive approach. And in the naive approach, we simply have the volume fraction covered of the feature. When the feature completely covers a finite element, it's 1. When it's completely outside, it's 0, where 0 means rho min, but this is ignored in this presentation. And when it's partially covering the element, the volume fraction is our pseudo density variable. And we scale our local element stiffness matrix by this pseudo density value as we do in topology optimization. This is what we get when we move the bar. And when we move the bar, we have positions when we are completely aligned with the mesh. Then we have a perfect black and white solution. And with this grayness measure, it means we have no grayness. Half an element wider, we have grayness. We have the intermediate volume fractions. And then again, no volume fraction, no grayness. So the grayness bumps. The sum of density is constant, but the grayness varies. And when we observe the compliance we get, we have the best compliance for small s, but we have these spikes in this magenta compliance curve. The peaks we have when we are aligned with the mesh, when we have no grayness. But this is what we would get for conforming mesh. But in between, when we have grayness, our compliance is significantly better, but it's too good. So it's not the realistic one. Conforming mesh would be realistic. And what we shall expect as an optimizer from such a behavior is strong non-monotonicity are local optima. Is it clear what I explained with the graph?
Yes, it is clear.
Thanks. Why do we have this grayness? For this, we go back to the very early time of our community. And you smile because this is your topic, I know. And in '88, Martin Benson and Noboru Kikuchi, they analyzed these porous structures with mathematical homogenization and observed what do our material tensor coefficients do as a function of the density, the volume fraction. And from this, Martin Benson came up with this power law approximation. And in 1999, Martin Benzo and Olli Sigmund wrote a very important paper where they really discussed in detail what does this material interpolation, this pseudo-density stuff mean at all. And the important baseline for me from this paper is this black line, which are the upper Husschen-Friedman bounds. And this is a physical bound. Nothing can be above. No, cannot have a better density to stiffness relationship. That means when we are linear, as we are here now with the volume fraction or with VTS or sim with P equal 1, we have an unphysical superpower material. We may not be surprised from the stiffness we get, from the compliance we get. So one slide about this material interpolations. The lineage we just had, the mustard colored is common sim to the power 3, and the blue are the physical Husschen-Friedman bonds. With the linear case, our compliance is too good whenever we have grayness. In the mustard rho to the power 3 case, our compliance is very poor when we have intermediate materials. It's penalized. But also in the blue case, we are not continuous. But this is what physics tells us. When we have isotropic intermediate material, it has a poor stiffness. But when we are below the conforming mesh and above the conforming mesh curve, there shall be something which is in between. And this can be found with the ramp function with a parameter of q equals 1. So what people do is they don't have the step function, but they have differentiable shape functions. And these shape functions have a constant amount of grayness, whatever constant means, whatever grayness means in which measure. And these boundary shape functions, for this we need a design distance function. We have a transition zone in elements. And when we send the pseudo density is now the integral of our boundary function. And the boundary function is 0 far away outside the structure, 1 far away inside the structure, and it's the boundary of the structure. At the transition zone, we have our function, which is here in dark green, a linear function, piecewise linear boundary function, polynomial function in blue, which is very close to a cosine function. And in light colors, we see the integrals at the elements. The upper graph transition zone 1 and the lower transition zone 2.
So did you employ analytical integration or different kinds? Okay.
Analytical integration. When we apply these boundary shape functions to our H benchmark, we see again with the red curve the step function we had before and the density values for it. We see that for the linear case in the green one, we are nicely smooth. So we have not much mesh dependency anymore. It's not as nice for the polynomial one. For the polynomial one, we need to have the case with a transition zone of 2 to have this nice curve. But here, the compliance is always better than what we would have for the conforming mesh.
So where do I see the data for the conforming mesh here?
It's not the data from the conforming mesh. It would be the connection of the peaks of the red line. What we see is the polynomial function with transition zone of only 1. So as we have for the blue curve, but here's the ramp function applied. That means the ramp function here minimizes the effect of the mesh dependency. And it also is quite close to what we would have for a conforming mesh, even if it's a non-physical interpolation. But I don't use the ramp function anymore in the rest of the presentation because almost nobody does it. So it's more comparable to what we do when I do the linear interpolation. But we know the drawbacks of it, especially that the compliance is always overestimated. People do not do and cannot do this analytical integration we had before. So in reality, we need a numerical integration, and the numerical integration means that now our rho E's are found as a weighted sum of boundary function evaluations at integration points. If we have linear or Newton codes, integration points does not really make that much of a difference. And when we apply this to the polynomial function with pure integration, midpoint, trapezoidal rule, and 3 times 3, we again have a very non-monotonistic effect, which we wanted to get rid of by using this boundary shape function. It's almost close to what we have for step function, only by having a too poor numerical integration. And this is what is my take-home message. We need a sufficiently high numerical integration, otherwise we get effects we would not expect. Where sufficiently high numerical integration either means we have more integration points, but in reality often it means we have a wider transition zone. It's a combination of transition zone and numerical integration points per element is what we need in the end. Here we have a look on why the numerical integration is so strange. Dark is boundary function, gray is an analytical integral of each element, and the light green is the weighted sum of the red integration points. Yeah, and we simply see for midpoint trapezoidal rule, when the distance of integration points is in the range of the transition zone where our function lives, that's simply much too coarse. The function, this graph is okay?
Yes.
It becomes worse when we go to numerical integration or to sensitivity analysis. It's a nice thing with feature mapping is that by chain rule, most of the gradient information comes from the SIMP problem. So SIMP mask, SIMP implementation, all the physics, all the function we can reuse. The only thing we need to add is the derivative of the pseudo density with respect to the shape function, which is easy in the numerical integration case because we have a weighted sum of the derivative of the shape functions. And what we see here is we fix the element, move the shape across the element, and we observe the derivative of the pseudo density with respect to the shape function. In the linear case, the derivatives are just the slopes. So we have a sum of weighted values of the slope, which is nothing we can make any continuous optimization with. We need to go to a smoother boundary functions. And here we have the polynomial. And this is, I would say, again, quite surprising when we are too low in discretization. The nice thing is that poor effects go a little bit away because we sum up all this gradient information for all densities for this few shape variables. So this averages a lot. We have it here. In dark, this is a boundary function. Dark green is the derivative of the boundary function. The boundary function is constant outside and inside, so the derivative is 0. That means everything happens within the transition zone of our gradient. And in midpoint and trapezoidal rule, when we have a distance between integration points, which is the transition zone, that's simply extremely too coarse to sample anything meaningful.
But if you have a look at the animation with 3 integration points, you still see that there is some error to the integration. So yes. Would you recommend to take even more integration points?
Yes, much more. Much more. Not only integration points, but also it's a little bit artificial that I have here such a small transition zone.
Do you have something like a thumb rule?
Yes, I have. And we see on the next slide. Here we have the example from before. The boundary conditions, I hope, are clear. The optimum is also clear. And we have 2 kinds of numerical integration. So we have the same problem, just change numerical integration. In the first case, 1 element transition zone, only midpoint. So we know now that it's really 2 cores. And in the other case, 5 elements transition zone and 8 times 8 points integration points. This is what we use as a rule of the thumb. Here for the simple problem, it would work with less, but this is where we feel confident. And we see we are much better in convergence just by having a proper numerical integration.
And is there a reason why you chose rho min to such a high number? Which could you even go lower, or does that have any effect on the numerics?
Yes, it has. It scales the gradient, but convergence is better with a higher rho min because in the initial design, the feature doesn't see the force and it doesn't see the support. It needs to find it first. Therefore, usually people start with initial designs where support and force is always connected. This improves in feature mapping convergence quite a lot. So to the summary, I wanted to demonstrate the impact of pseudo-density, something we always work about with, but to remind us, did we really understand what pseudo-density means and what does the interpolation of the material really means? Talk about boundary shape functions, why we have them, how they work, and what is the important point for me is that when our numerical integration is too poor, we may lose a lot of what we expect from our boundary shape functions. As a conclusion, I think we shall really always be aware on what parameters we use. So that means for numerical integration, which transition zone we use, which number of integration points we want to pay the effort for it because it becomes expensive. Also gives these numbers in publications. But when we do it well enough, in our experience, we improve convergence by better numerical integration, and we can even escape poor local optima. So we can get better solutions by better numerical integration. And this, you ask, is our best practice value. Thank you very much, Nock.
Thank you very much, Fabian, and I hope to meet all in the session.
Me
too.
Ja.
Wie viel war es jetzt? In the presentation.